Think about how your brain works when you walk into, say, a busy room. You instantly get the gist, right? Where people are, the layout, maybe a few key things jump out. You're not meticulously analyzing every single tile on the floor. Your brain just focuses. It's incredibly efficient.
Absolutely. And that's exactly the kind of efficiency we're chasing in computer vision, especially with these models called vision transformers or ViTs. They've been game changers, honestly. Huge leaps in object recognition, scene understanding, you name it. But there's a catch.
Right. That power doesn't come cheap, computationally speaking, particularly when you feed them high resolution images. To see the details, you need lots of small image patches or tokens. And the more tokens, well, the more work the ViT has to do. It gets really expensive fast, a major roadblock.
Precisely. And that computational bottleneck, that's the exact problem tackled by the paper we're digging into today. It proposes a new approach called AnchorFormer.
Okay, AnchorFormer. So for this deep dive, we're not just scratching the surface. We've got the paper, we've got notes. We're going to really get into the nuts and bolts, not just what AnchorFormer is, but the how and the why. What are the core ideas? How does it actually solve that efficiency problem? Let's get into it.
Okay. So the source of the problem in, your standard vision transformer is the attention mechanism. Specifically, it's the global self-attention.
Self-attention, that's the magic sauce, right? Where the model figures out how every part of the image relates to every other part, gives it context.
Exactly. It's powerful. But think about it. If you have and tokens or patches from your image, a traditional VT calculates the relationship between every single pair of those and tokens. The cost of doing that scales quadratically with the number of tokens. We call that O.
Oh, okay, that's the big O notation, quadratic, meaning if you double the tokens, maybe use a bigger image or smaller patches for more detail, the computation doesn't just double, it quadruples.
That's right. It explodes. Go from, say, 1,000 tokens to 2,000, and you jump from roughly 1 million calculations to 4 million. It just becomes computationally infeasible really quickly, especially for large images or, if you don't have super powerful hardware. The paper nails this down as the key barrier.
And people have tried to fix this before, haven't they? Tried to make attention less global.
Oh, absolutely. There are approaches like sparse attention. Think models like PVT. They try to be clever and only calculate attention between certain pre-selected pairs of tokens. But the paper points out a potential issue. What if the really important information, the pivotal regions, are scattered randomly? You might miss crucial connections if you're too selective up front.
Okay. Or things like window attention, like in Swin transformers, where attention is local inside small windows.
Yeah, that helps efficiency within the window. But then you have the problem of figuring out how information gets between the windows. How do you stitch together that local understanding to get the big picture? It adds its own complexity. The paper kind of shows this conceptually in Figure 1. These methods have limitations compared to true global awareness.
So the challenge is getting efficiency without sacrificing that global context. How does AnchorFormer approach this? What's their big idea?
AnchorFormer introduces this really neat idea, anchor tokens. Imagine a small, manageable set of special tokens, let's say M of them, where M is way smaller than M, the total number of image tokens. Think of them as representatives.
Like those key things our brain zooms in on, the important bits.
Exactly like that. And this leads to their first big innovation, anchor-based bipartite attention. Instead of calculating attention between all image tokens and all other tokens, the open source nightmare AnchorFormer does something different. It calculates attention only between the small set of M anchor tokens and the large set of image tokens.
Okay, wait. So it's attention, but it's connecting two different groups. The anchors on one side, the image tokens on the other.
Precisely. That's why it's called bipartite attention. It connects elements from two distinct sets. And this fundamentally changes the math. Instead of n times n, it's m times n. The complexity drops from OOA down to O and n. Since m is much smaller than n, that's a huge saving. The paper states it clearly. The complexity will be reduced from OA to OEM, where M is an anchor number and MN.
Okay, OEM. That's much better. Step 1, use these anchor representatives for efficient attention. But how do you choose the right anchors? If they're just random, it might not work well. And also, if attention is only between anchors and tokens, how do you still get the global picture? How do you know how image token A relates to image token B? Didn't we lose that?
Excellent questions. And they lead directly to AnchorFormer's other two key innovations. These are really the clever parts, academically speaking. The second innovation is the differentiable learning anchors. This is super important. The anchors aren't just picked randomly or fixed beforehand. The model actually learns what the best anchors should be.
Learns them. How does it learn an abstract anchor?
Well, the paper explains they represent these anchor tokens using neurons in a neural layer. They become part of the network itself. Because they're part of the network, their values can be adjusted during the training process using standard backpropagation and gradient descent. It's like the network tries some anchors, sees how well it performs the task, like image classification, gets feedback, and then tweaks the anchors to be better representatives next time.
Ah, so it's data-driven. Instead of guessing what's important, the network figures it out based on what actually helps it solve the problem.
Exactly. The source uses the phrase differentiably and accurately learn the pivotal regions distributed randomly in the input images. It's about the model learning to capture the distribution of important information, wherever it might be. They mention some math inspiration, but the takeaway is the anchors are dynamic, learned, and optimized. A big step up from fixed anchors.
Okay, so we have efficient attention using learned anchors, but what about that global picture, the token A to token B relationship?
Right, that's the third major innovation, using the Markov process idea for global attention. Even though the direct calculation is bipartite, anchor to token, the goal is still to approximate that full global self-attention. To do this, they took inspiration from the concept of a Markov process.
Markov process, isn't that where the future state only depends on the current state, like memoryless? How does that apply here?
It's more about the structure of transitions. Think about getting from state A to state C in a Markov chain. You can figure that out by considering all the intermediate states B you might pass through. So A to B, then B to C. They apply a similar logic to attention. The idea is the similarity or relationship between two image tokens, let's call them token A and token B, can be estimated by looking at how they both relate to the anchors.
Oh, I see. The anchors act as the intermediate hubs or states.
Exactly. If token A strongly relates to anchor 1 and anchor 1 strongly relates to token B, then A and B are likely related even if we didn't compute their direct link. By doing some clever matrix math, rearranging the order of multiplications, as they mentioned conceptually around equation 13, they can calculate an approximation of the full token A to token B similarity matrix.
And crucially, they can do this calculation without going back to OM complexity.
Yes, that's the beauty of it. They get this approximated global attention matrix, but the calculation still has that efficient own linear complexity. The paper notes, by rearranging the multiplication orders, it obtained the linear complexity, such as O and N. So the whole AnchorFormer block, which you can see in their figure 3, isn't just a downgrade. It's using learned bipartite attention efficiently and a Markov-inspired trick to recover the essential global relationships, all while speaking the computation lean. It's pretty sophisticated stuff.
Wow, okay, that is clever. Efficiency, learned anchors, and approximating global context via this Markov idea. Quite a combination. So the theory sounds good. How did it actually perform when they tested it?
They ran it to the gauntlet, basically. The standard big computer vision benchmarks, image classification on ImageNet, object detection on COCO, and semantic segmentation on ADE 210K. Covers the main tasks.
All right, let's start with ImageNet classification. That's kind of the classic VOT benchmark.
Yep. And looking at the results, like in Table 1 and Figures 2a and 5, AnchorFormer looks really strong. The key metrics here are usually top 1 accuracy versus the computational cost, measured in FLOC's floating point operations.
And AnchorFormer seems to do well on both, hitting a good trade-off.
It really does. The paper makes a pretty strong claim saying AnchorFormer consistently achieves the best performance than the others in terms of accuracy and efficiency. They specifically call out a comparison between their AnchorFormer B model and another efficient model called biFormer B. Get this. AnchorFormer B achieved up to a 9.0% higher accuracy or 46.7% floating point operations, FLOPs, reduction on ImageNet classification.
Whoa, hold on. Nearly 10% more accurate, or almost half the computation. That's a huge difference.
It is. Those specific numbers are impressive. AnchorFormer B gets 86.62% top 1 accuracy using just 9.2 GigaFLOPs. biFormer B, for comparison, needed 15.5 GigaFLOPs and only reached 84.42% accuracy. And their figure 5 shows it consistently beating other models like Digo and Levit, higher accuracy for fewer FOPs across different model sizes.
Okay, solid on classification. What about finding objects? Object detection on COCO.
Similar story there. Table 2 and Figure QP show the results. The metric is MMAP, mean average precision. AnchorFormer delivered significant MMAP improvements compared to established detectors like YOLO, EfficientDet, even FPN v5, often with comparable or fewer FLOPs.
Any numbers jump out.
They report MMAP gains in the range of 30.0%, 81.3% versus those baselines. Table 2 even shows it performing well against models specifically designed for mobile efficiency, like MobileNet variants. So the efficiency holds up in detection tasks too.
And the third one, semantic segmentation. Assigning a label to every pixel, right? On 80E210K?
Yep, Table 3 shows the trend continues. They plugged AnchorFormer in as the backbone, the feature extractor for standard segmentation methods like semantic FPN and UpperNet. Compared to using other backbones like PVT or SWIN, AnchorFormer generally led to better MIOU, mean intersection over union, the standard metric here, and better efficiency. For instance, compared to using PVT in one setup, AnchorFormer needed 14.4% fewer FLOPs, but achieved a 2.3% higher MIOU.
So it's consistent then. Better accuracy, level computation, across classification, detection, and segmentation. Did they show anything visually, like where the model is looking?
They did. Figure 4 has some GradCam visualizations. These are heat maps that try to show which parts of the image of the model paid most attention to. And the visualizations suggest AnchorFormer is indeed focusing on the relevant objects or regions in the images, which supports the idea that it's learning to identify that pivotal information effectively.
Nice. Okay, beyond the main results, you mentioned the paper has ablation studies. I always find those useful. They help prove which part of the new model is actually responsible for the improvements.
Exactly. Ablations are crucial for validating specific design choices. The first key one they did, in Table 4, was to test the value of the differentiable anchor idea itself.
How did they test that specifically?
They set up a comparison, a baseline vanilla VMIT, then a version where they added anchors but kept them fixed, a basic anchor VMIT, and finally their full AnchorFormer with the learned differentiable anchors.
And the learned anchors really made the difference.
Big time. The paper states, compared with the basic anchor vision transformer, the differentiable model obtains 22.2% FLOPs production and 4.5% top 1 accuracy improvement. That's a pretty direct confirmation. Letting the network learn the best anchors wasn't just a theoretical nicety. It directly led to lower computation and higher accuracy compared to using fixed anchors. It validates that core innovation.
Makes sense. Did they also look at the number of anchors used? I guess M, the number of anchors, would be important. Too few might not capture enough info. Too many might defeat the purpose of efficiency.
You nailed it. Table 5 explores exactly that. They tried using different numbers of anchors, 10, 30, 50, and 100, and they found, there's a sweet spot. Around 30 anchors seemed optimal for the specific models and tasks they tested.
And why is there an optimal number? What's the reasoning?
The paper explains it quite intuitively. 2 less anchors may discard some features and drop the performance, basically not enough capacity to represent everything important. But too many anchors also introduce redundant information to limit the performance. You lose some efficiency benefits and might even add noise or dilute the important signals. So it confirms the anchor concept works, but like many hyperparameters in deep learning, the exact number needs some toning to get the best trade-off.
Okay, so putting it all together, AnchorFormer seems like a really well thought out approach. It builds on VTs, but tackles that core problem head on. It uses this clever combo of efficient bipartite attention, makes the crucial anchors learnable, and then uses that Markov process idea to approximate the global view.
Yeah, it's a solid piece of engineering and research. And it's interesting to note the authors come from a mix of places PetroChina, universities like HKU and SCUT, shows how these ideas often emerge from collaborations across different sectors.
And they even mention potential future work applying this.
Right. They suggest the efficiency gains could be really useful for things like analyzing high-resolution images of ancient texts or maybe archaeological artifacts, areas where you need fine detail, have potentially large data sets but might not have unlimited computing power. AnchorFormer's agency could be a great fit there.
So wrapping up this deep dive then, AnchorFormer offers a compelling solution to the vision transformer efficiency problem. The key takeaways are its innovative use of learned, differentiable anchors for efficient bipartite attention, and the smart application of the Markov process concept to approximate global interactions without the quadratic cost, all leading to strong performance across major vision tasks.
Exactly. It really validates those core academic contributions, that learning the pivotal information distribution is key, and that complex global patterns can be approximated efficiently through these learned intermediate representations, the anchors.
And they leave us with something really interesting to chew on for the future. Right at the end, they mention exploring a connection between this anchor attention and something called positive incentive noise theory.
Yeah, that caught my eye too. It's a fascinating direction. They suggest that maybe the learned anchor attention, because it's an approximation of full attention, could be viewed through the lens of this theory. Positive incentive noise theory basically explores how, counterintuitively, sometimes noise or variability in a system can actually be beneficial or provide a positive incentive for performance.
Huh. So instead of just thinking of the approximation error or the noise and the learned anchors as purely a bad thing to be minimized, the idea is maybe we could understand it mathematically, maybe using this theory and find ways to actually leverage it. Could the inherent randomness or variability in how the model captures information actually be harnessed?
That seems to be the suggestion. It kind of flips the perspective. Maybe the path to even better, more efficient attention isn't just about reducing error, but about understanding the nature of that error or variability, the noise, and perhaps even using it strategically. It hints that the next breakthrough might come from a deeper understanding of how noise and approximation interact in these complex learning systems. A really provocative thought to end on.